This
Hello,
conference
Krishnamurthy.
will now be recorded.
Yeah, good morning, dear students. In the last class, we have seen the Ponchon-Savarit method, and by which you can able to estimate the number of theoretical stages in continuous fractionating column. And now again, let me repeat the comprehensive method of the Ponchon-Savarit to estimate the number of theoretical stages in the distillation column. So, as all of you know that the there will be enthalpy concentration diagram by which you can able to find out the number of stages in using Ponchon-Savarit method, because Ponchon-Savarit method will not have any assumptions, and also it will allow us to estimate the energy requirements for the given separation. So that is the way Ponchon-Savarit method will be more useful than the Mercaptile method. Mercaptile method will give you only the qualities and quantities of the streams, as well as its purities, but it is not talking about the energy requirements. Whereas Ponchon-Savarit method will not have any assumptions, so it will give the energy requirements also. So all of you know that distillation column and its sections, continuous distillation column and its sections, top section, bottom section, and reboiler, condenser, etc., and also feed tray. So usually here you can see this top one is the enthalpy concentration diagram, which can be drawn by using enthalpy values at a given liquid mixture, as well as the vapor mixture. If the liquid mixture is a saturated liquid, then all the points at a different concentration will fall on this line, so it will become the saturated liquid line, so which is drawn with the saturated liquid compositions as well as its enthalpies. Enthalpies means the heat contained by the saturated liquid mixture, and this is also a line which gives the saturated vapor enthalpies versus its concentration. So these two lines are there. So in any method, the first you have to find out the minimum reflux ratio. So let us know that minimum reflux ratio, how you can able to find out. So even though I explained in the last class, let us see here also. For example, you have one, the specifications in the column where you have to get the product purity of this much concentration. Let us say it is 0.89 or 88, like that. So this is the concentration of the top product purity, so that you require. So for this, let us find out how much will be the minimum reflux. So to know the minimum reflux, you should also know the feed composition. So feed composition is around 0.42, and then this is the enthalpy contained by the feed, and you can also say that it is meeting here, so that means it is a saturated liquid. So saturated liquid feed and having a this much product purity, you have to separate in a distillation column. Then how much minimum reflux do you require for this case? So let us see that. How do you find out? First you have to draw this line, a vertical line at XD, and an XF also you have to draw, so that you will know the corresponding enthalpies. This is the enthalpy of the feed, HF, and this is the enthalpy of the vapor, which will be obtained at the top column, and this will be the enthalpy of the uh, uh, reflux, which is sent back. So both are at saturated condition, because let us say you are using the total total condenser condition. Under the total condenser condition, xd is equal to y1 and y1 is equal to xl0. That means the top product quality composition will be matching with the vapor composition which is entering into the condenser, and also the reflex composition which is sending back to the column. So that's why we call it as a total reflex condition. Then only you can draw this vertical line. So under the total condenser condition, and you can say that a saturated liquid feed is used, and the composition of the top product which you require is xd. Then how to find out the, so the XY diagram which will give the corresponding vapor liquid equilibrium compositions. See, when you draw these two lines, one is at XF and another is XD, then you can just find out this X corresponding value on this diagram by drawing this one. So you will get the corresponding the uh, enthalpy, also its composition which is equivalent with the xf value. You can call it as this is a yf, because you have to draw one pinch point. Pinch point means the xf should be equilibrium with the yf value. Such yf value you can find out. Then you can just find out by joining these two. You can draw a line. So that line is called a pinch line. This line is called pinch line. Pinch line means if this is matching with this equilibrium point. See, these are the equilibrium point. So one equilibrium point will give you the 2 points on the HXY diagram. So this is a equilibrium or a tie line. So the operating line which goes through the tie line, that means it is a pinch situation. There is a pinch situation. So that gives the, on this diagram, QD prime minimum. So this is the minimum condition at which you have to supply the reflux ratio for getting this much of the separation. So you will get QD minimum. So these two, because it is a total condenser condition, the vapor will be getting just removed its latent heat of vaporization lambda to get the saturated liquid, from saturated vapor to saturated liquid. So the value is called the lambda of the product mixture. This is the lambda of the product mixture. So this is equal to that. Then when you estimate this height, so this height is equal to R minimum into lambda. So from this, after measuring this height, you can find out the R minimum. That is how you can find out the minimum reflux ratio. So once you find out the minimum reflux ratio, then you can multiply this minimum reflux ratio either 1.5 times or 2.5 times. So again, you can find out actual QD minimum. Then actual QD minimum will give the another F line. So that can be drawn. So that we'll see in the next case. So here, to find out the minimum reflux ratio by using the saturated liquid feed, then the R minimum can be found out by measuring this line. So you have to draw one pinch situation, and from that you can able to find out R minimum. I think this is very clear to everybody. If you have the feed is saturated vapor, this is another case. So in case of the saturated vapor, so you have to take on saturated vapor line. So it is intersecting here. So this will give you the corresponding feed which is in the saturated vapor state, its enthalpy. So from here you have to draw one pinch point. So pinch point how to draw, and you just find out this one is coming here, and then you have to find out the corresponding X. From here you have to find out corresponding x. So the corresponding x is here. So if you think this is yf, then xf is found from the equivalent data by drawing down and extrapolating onto the equivalent line and sending back. So then again you can just draw one line which goes through the YFHV, and this is another pinch situation for a saturated vapor feed. So you can draw the pinch situation for a saturated vapor feed, and this is a pinch condition for the saturated liquid. This is the pinch condition for saturated vapor feed. So for saturated vapor feed, your QD minimum will be this value, not this value, this value. So the QD minimum is increased. QD minimum is increased. Therefore, R minimum also will increase. R minimum will also increase to this level. So lambda is constant and R minimum will increase. So you can say that the minimum reflux ratio increases if the feed mixture enthalpy, because here you see the feed mixture is initially having this much of enthalpy when it is in the liquid state. Now it is a vapor state. So the feed mixture enthalpy increases. So when the feed mixture enthalpy increases, what is happening? Minimum reflux ratio also increases, because R minimum should be more to get this point, because keeping lambda constant. Therefore, you can make this conclusion. What is the conclusion? Minimum reflux ratio increases if feed mixture enthalpy increases. If feed mixture enthalpy increases means feed is changing from saturated liquid to saturated vapor feed, then the enthalpy increases. And also you can see that the condenser load, this is the Q minimum is initially here. Now it is increasing to this one. So what is this? This is HD minus HD minus HD plus QD by or QC by D. QC by D. This is the value. So that means the condenser load increasing. So when minimum reflux ratio increases if the feed mixture enthalpy increases. So this is one way. If the feed mixture enthalpy increases, then the condenser load also increases. So what we can say that if the situation is changing from saturated liquid feed to saturated vapor feed, so what you can observe in the continuous distillation column, the condenser load also increases. As reflux ratio increases, the condenser load also increases. But however, you can see that reboiler duty. How do you find out reboiler duty? By making at XW1 line, and see, this is the your value of 1 minute. I'll explain again. Just a minute. Yeah. So again, you can see that how this can be drawn. Saturated liquid, and yeah. Now here you see, if you draw at XW, so these lines can be extended onto these. These lines can be extended onto this, and you can find out the uh, QB value. QB value is the reboiler duty. So for the first case, reboiler duty is more, and the second case, reboiler duty is less. So therefore, you can conclude that when feed mixture enthalpy increases, reboiler duty decreases. If the feed is changing from saturated liquid to the saturated vapor, so you can say that reboiler duty increases, whereas condenser load increases, and minimum reflux ratio increases. While these two are increasing, only this will decrease. In certain cases, you can see that if the saturated vapor is used, then you don't require the reboiler at the bottom also, because it doesn't carry any reboiler, because it is having more sufficient heat. So that decision also you can take. Okay, so you should see the XD values and XF values as well as XW. You can find out the minimum reflux ratio for the two cases. And another three cases are there, because we know when the enthalpy is falling here, it is a superheated vapor. It is falling in between. It is a saturated vapor plus saturated liquid. If it is falling below of this, it is a subcooled liquid. So we'll see in the subcooled liquid state. So you again you see, for the case of the superheated vapor and subcooled liquid, how to find out the minimum reflux ratio. Okay, just see, this is again XD and this is XF. Then you see, you are having initially, I'll tell you, you are having initially here, F is here, XF HF is here. So this is the, what is the state of the feed? State of the feed is subcooled liquid, because it is having a lowest enthalpy. The feed is carrying lowest enthalpy, so it is called subcooled liquid. At subcooled liquid, if you want to draw one operating line, how to draw? This point and this point should match on the equilibrium line. So how to draw that? So first you draw this line, then you see, you can see one point here which is falling on equilibrium curve. Again you can see this, and then yeah. So this line, which is a pinch line, the pinch line which you are drawing, that should adjust such that these points, when you bring down to this line and this line, both should intersect on the equilibrium line. Such a try and error method has to be used to draw the pinch point. So this is a one pinch line which you have drawn, which is going through the F, and this is the Q minimum. And see that now this is anyhow lambda, only very small value will be there. So R minimum will be very small, because this much height only it has been increased. So for the subcooled liquid feed, you can say that R minimum is very low. And again you can take the saturated vapor, for example, this is sorry, superheated vapor. So you see the point is above the this line, this line, just above this line, means it is a superheated vapor. And then you can find out this much of enthalpy it is carrying. So this enthalpy is more than the saturated vapor enthalpy. That's why we are calling it as a superheated vapor feed. Then you can just see this line coming down to this one and coming here, like here, and we are trying to draw a pinch point or pinch. See, this is exactly matching with the equilibrium point, therefore this is called a pinch point, and this pinch point can be extended here, so that you can find out a QD minimum for a superheated vapor feed case. So it is a very high, so this much height you have to give. That means the condenser has to take lot of load, it has to remove heat more heat than the saturated vapor case. So this is again a pinch point. Why it has become a pinch situation? Because these 2 points are, when you come down on this line and also on saturated vapor line, both when you come down, they are meeting on the equilibrium point. Therefore, this has become a pinch point. So pinch line as well as the operating line, both are on the same straight line. Therefore, it has become a pinch situation for the superheated vapor. So this will give again QD minimum when the feed is superheated vapor. Similarly, you can also say that if the feed is both, see here, the feed point is falling here. So when it is falling, you have to draw one line such that, and this point again, and this point should meet on the equilibrium line. So this is the feed enthalpy, which is having a both a portion of the saturated liquid, a portion of the saturated vapor. Then you can see this point and this point when you draw to down, so they should meet on the equilibrium line. So if you are unable to get, just adjust these lines such that they will be meeting on this line. So such a pinch line you have to draw. So again, this is going, when the feed is saturated vapor plus saturated liquid, this is going on the going through a tie line. So that means it is a pinch situation for the saturated vapor plus saturated liquid. So this is a superheated vapor feed, and this is a subcooled liquid, and this is saturated vapor plus saturated liquid feed. So you can say that the minimum reflux ratio is maximum for the superheated vapor, minimum for the subcooled liquid. So you can put a descending order for the minimum reflux ratio. The minimum reflux ratio decreases when the feed is coming from the superheated vapor feed to subcooled liquid. So in between you have saturated vapor and saturated liquid. So 5 lines you can write down. So the minimum reflux ratio is greater for the superheated vapor, and then a little lesser for the saturated vapor, and saturated vapor plus saturated liquid is lesser than this case, and then the saturated liquid is still lesser than this one. For subcooled liquid, it is a smallest reflex ratio. And condenser load also you can put the same order, but reboiler duty will be inverse. So this is how the minimum reflex ratio can be estimated for various feed conditions. So if XD varies, you can also see that, suppose for the case, let us say in a previous case, just a minute, I will just, yeah, yeah. In this case, this is a saturated liquid. Let us take the saturated liquid case. For example, usually the curves will vary like this. When the concentration is low, more volatile component concentration is low, so the lambda value is high. When the concentration of the low volatile component, more volatile component is low, then the lambda value also low. So uh, more volatile component is more, lambda decreases. More volatile component less, lambda increases. So higher value for the dilute, you can say that dilute mixture, high lambda value will be there. For concentrated mixtures, low lambda value is there. Therefore, if you want more concentrated product feed, let us say for a fixed condition, if you want more product concentration, that means lambda XD value comes this side towards the one, when it comes towards the one, so what is the decreasing? You can see that lambda value is decreasing. So when the lambda A value is decreasing, so what you can say that the R minimum by lambda value will also decrease. So R minimum will be decreasing when the XD value is increasing. So similarly, if you go this side, then the lambda value increases. So you can say that R minimum increases. So it does depend on the product purity also. So finally, what you can conclude out of these two slides which I explained now is the minimum reflux ratio does depend on the type of the feed, and also the XF value Okay, and then the product purity. So these three are variables on which the minimum reflux ratio does depend. So you can also say that condenser load and reboiler duty also will be depending on that. So if you want more XD, then you can have a more reboiler duty because the RM decreases, so this will be increases. R minimum increases for that case. So you can analyze in that way and find out what are the different optimum parameter in continuous distillation column. So similarly, we will be seeing in the next one, next slide. Yeah, yeah. This is the estimation of the theoretical stages. Let us see for a complete distillation column how we will be estimating this. So first you have to draw XD as I told, and you know the R value, then you can find out this one by multiplying the R into lambda, then you will get this one, and F can be added such that I will just tell again. Yeah. So yeah, yeah, this is this one, and you can then draw D versus F. So W will be obtained at XW. Then at F you can draw one line. F is a saturated liquid. That's why it is falling here. So first you can draw the first tray will be here. So you know the XD is coming. So it will be coming to this one. So this will be first tray, and then operating line will be added. Then again it come down to this one, then you will be getting a L1, L2, L3, then you'll get the second tray, then the third tray, then we will come from this side is like reboiler will be coming like this, and then this will be operating line for the stripping section, then the lowest stage, then the operating line, then from year to year can draw one line, then this line can be increased years, then you'll get this one, and then another operating line. So you will be getting step by step. So another one. Yeah. So like that you can able to draw the number of stages which are required in a theoretical required in a continuous distillation column. So total you have got 1, 2, 3, 4, 5, 6 plus one is the reboiler, and also the feed will be entering from the fourth stage from the top 1, 2, 3, 4. So here the feed is entering. So you can find out as a whole the number of theoretical stages and in which stage again it is entering. So please watch carefully. Again, I will be just drawing this one. Yeah, you please see that. So first you are drawing this lowest curve. Yeah, this is the XY HXY diagram. Then X. Okay. Then you will be drawing the feed line. This is called the feed line, and that is XW line. Then the again the feed line onto the XY diagram. Then you will start from here, this one. Yeah, here it will be going. So this is the first stage. Then this will come the operating line for the second stage. Then you will come down here, go here, then you are coming. So this will be second stage. Then again you draw the operating line. Then the third one, yeah, it will go here. So coming to this one, yeah, L3 will be obtained. So this is the third stage which you can able to draw, and you can also draw one more line, but we have started from the bottom. So this is the reboiler operating line. Then again you draw the this one. Yeah, this is the lowest stage. Then operating line. Then come down to this. Yes. Then you will go up. Yeah. Then yeah. This is from the bottom. This is after reboiler second stage. Then you will be having, yeah, this is the third stage. So this is how you can able to draw the number of stages in a continuous distillation column. So I think it is clear to everybody, isn't it? And similarly, you can draw the here, the minimum number of stages which are required. This I need not to explain. I have already explained. Now all of you, please take this particular problem, and this gives the, I will read, you please note down, or you can also take a picture of it and solve this one. I'll just read this one. A total of 100 gram mole feed containing 40 mole percent N-hexane and 60% N-octane is fed per hour to be separated at one atom to give a distillate that contains 92% hexane and the bottom's 7% hexane. A total condenser is to be used and the reflux will be returned to the column as a saturated liquid at its bubble point. That means the reflux as well as the feed are saturated liquid state, means they are at its bubble points. So a reflux ratio of 1.5 is maintained. The feed is introduced into the column as a saturated liquid at its bubble point. Use the Ponchon-Savarit method and determine the following: minimum number of theoretical stages, the minimum reflux ratio, the heat loads of the condenser and reboiler for the condition of minimum reflux, the quantities of the distillate and bottom streams using the actual reflux ratio. So I have given the VLE data as well as enthalpy concentration data. So first you have to draw this one. So HXY diagram you can draw, and below that, and match with the XY same scale, you can draw XY diagram also. So both the diagrams you keep ready, and then you can able to do this problem. So I suggest all of you, because I have to visit the exam portal again to observe the invigilators as well as how the exam is going on. So I will just do that. Meanwhile, you can solve this problem, and maybe by evening you can upload, because I will be posting this in the Google Classroom. So you will just post this one. Okay. So hello, please stop the
Yes, sir.
recording. Yeah.
Okay,